everyone, it's Miss Seward. Today we are going to learn about primary productivity. Now, the learning objective for today is going to be explain how solar energy is acquired and transferred by living organisms. And some of the essential knowledge that you're going to gain from these notes are primary productivity, how it relates to sunlight and photosynthesis, the gross primary productivity in an area versus net primary productivity, how it is that we measure and calculate it, and then the skill that you are going to practice by the end of this is describe environmental concepts and processes. So let's start with some primary productivity basics. Now, the definition of primary productivity is the rate that solar energy is converted into organic compounds via photosynthesis over a unit of time. Now, if we look at the units for primary productivity, one example would be kilocalories per meter squared per year. And again, that's going to be energy in an area over a unit of time, which relates back to that definition of primary productivity. Now, sometimes I think it's a little bit simpler to actually just think of it as the rate of photosynthesis of all producers in an area over a given time, because the rate that solar energy is converted into organic compounds via photosynthesis, basically think about if you look at this certain area, what is the rate of photosynthesis? And another way to think of it is because photosynthesis leads to growth, you can also think of primary productivity just as the amount of plant growth in an area over a given period of time. So especially when you're kind of visualizing different biomes or areas and trying to think of the primary productivity, you can also just think about like how well do plants grow here. Now, if we have a high amount of primary productivity, that means you have a high plant growth. So you have lots of food, you have lots of shelter for animals, which is why ecosystems with high primary productivity actually are usually more diverse. There's a lot more biodiversity. So they have a diversity of species. You have a lot of different types of plants and animals and bugs. And you're going to have the high primary productivity areas are going to be more diverse than ecosystems with low primary productivities. So if you think back to our biomes, think about a rainforest versus a tundra. Rainforest is going to have higher primary productivity, and it's going to be way more biodiverse than what you're seeing in a tundra. Now, when it comes to primary productivity, we actually do calculate it, and there's a few different aspects into calculating it. So we first start with the gross primary productivity, which is abbreviated as GPP. And this is the total amount of sunlight that a plant captures and converts to energy in the form of glucose through photosynthesis. Now, if you're somebody who has a job and you have ever looked at that paycheck, I'm going to give you kind of a comparison that helps me to think through it. So if you're looking at gross primary productivity, think of this as like the total paycheck that a plant earns. Like everything, the amount of sunlight that they're getting, that they're converting to glucose. Then we have respiration loss. And this is the idea that plants use up some of the energy that they generate from photosynthesis by doing cellular respiration. Because remember that plants do photosynthesis and cellular respiration. So they use some of that energy. They also use it through like movement, internal transportation, and things like that. So you can think of respiration loss as sort of the taxes that a plant needs to pay. So if you think of the paycheck that you get, you always have that gross amount and it looks way bigger. That's the first one. And then you have the taxes that you have to pay, which is similar to your respiration loss. Then we have the net primary productivity. And this is going to be the amount of energy, or we can think of it like biomass, which is left over for consumers after the plants have used some for respiration. So continuing to go with this paycheck analogy, this would be like the actual amount of the plant's paycheck after all the taxes have been taken out. So again, you think of some of your paychecks, you've got that big amount, you've got taxes, and then you have the smaller amount that actually is what gets deposited into your bank account. That's going to be some sort of like your net primary productivity after everything has been taken out that the plant ends up needing to use. So if we're going to calculate primary productivity, it is going to be the gross primary productivity minus the respiration loss, and that's going to give you your net primary productivity. So if we look at a diagram here, you think of the photosynthesis that comes in, which is going to be the total energy captured. Respiration is going to take a chunk of it, the energy that's used up, which is lost as heat. And then you have the actual energy that's left over after that is the net primary productivity. So this leads us to ecological efficiency. And ecological is we're starting to zoom out and look on the whole like ecology system side of things, not just the individual plant. So you have the portion of incoming solar energy that is captured by plants and then converted into biomass, which is the net primary productivity, or basically it's the food that's going to be available for the consumers. So the sun shines its light, the plant takes it in, it uses some of that, but it ultimately also creates glucose, makes more leaves, makes more stems, and then what's left is going to be the food that's available for others who might come along and eat it. Now, generally, only about 1% of all incoming sunlight is captured and converted into your gross primary productivity via photosynthesis, which is crazy. You think of all of the plants here on planet Earth, and only about 1% of sun's solar energy is being used by those plants. Like, that just blows my mind a little bit. Anyway, so if you look at this diagram here, 99% of the sun's energy is being reflected. It passes off, it doesn't get absorbed, and 1% of that then is hitting the producers and being captured by photosynthesis. Now, of that 1%, only about 40%, now if you're following the original math, like 0.4% of the total sun solar energy is then converted into biomass or plant growth or the net primary productivity. So of the 1%, 60% of it is lost to respiration, and then 40% ends up being left over to potentially be used for food for that net primary productivity. Now, some ecosystems are going to be more efficient, so they will have a higher net productivity than others. So these numbers that I'm giving you, they're kind of more estimates or averages. It's not an exact rule that every single ecosystem in every single situation will follow. So sort of keep that in mind that some are a bit more efficient than this. But we do see trends in productivity. Now, generally, the more productive that a biome is, it means the more amount of diversity that an animal life that it can support. So you have high biodiversity. So if you kind of think about the biomes that we've learned about, try and predict the most and least productive terrestrial and aquatic biomes. So the more productive, you're going to have more biodiversity. So if you think of the biodiversity of some of these different biomes that we learned about, what might have the most and what might have the least. And this is a reminder of some of those ones that we learned about. We got the terrestrial ecosystems on top. We've got the marine ecosystems on bottom. So some other factors that do lead to high net primary productivity is going to be water availability, higher temperatures, and nutrient availability. It doesn't really matter if you have tons of sun but no water, your plants are not going to thrive in that environment. So there are some other aspects coming into productivity. It's not purely just solar. So if you go and you start thinking about that high biodiversity, your areas on this here that have high net primary productivity, it's going to be your swamps and your marshes and your tropical rainforests. Then you're also going to have your coral reefs and your salt marshes. So if you look at the net primary productivity here on the axes, you're going to see that these ones end up having more. So hopefully that's what you got right for that question earlier. Now, shortages in water availability or temperatures or nutrient availability are going to lead to decreased net primary productivity. So an example would be a desert. Deserts get lots of sun, but they don't have much water and they don't have much nutrients. So that is going to limit the primary productivity even though it's warm there. Or another example is going to be the tundra. Your water is frozen. It is very cold. So even if you don't have many clouds and you have sun shining all day, plants are still not going to be able to thrive in this environment. So you're going to have a low primary productivity amount. And then another example is going to be the open oceans, which are going to have your low amounts of primary productivity. Now, if you want to go back and review some of the biomes in the biome notes that we did, which is 1.2 and 1.3, I did talk about primary productivity in each of those slides. So you can go back and reference the productivity in it. So that can kind of be a refresher if you would like to go back and revisit some of the biomes that we talked about then. What you are going to be doing for your practice FRQ is you are going to describe the process of net primary productivity, and then you are going to describe the relationship between primary productivity and biodiversity. And those were your notes on primary productivity, and I hope you learned something.